तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were talking about the different levels regarding the memory hierarchy, namely cache, DRAM or main, and then storage or disk subsystem, for instance. So, we said that CPU generally addresses cache and tries to look for the required data there. If it is not available, then there must be some mechanism by which from the main DRAM memory the information is brought. And we also define in the previous lectures that a block of data is the minimum unit of data that is passed between any two levels for that matter. Okay. Normally you can take it that we always talk about CPU and then two different levels such as CPU and cache and DRAM. We may not very much go into the other one because there are other issues when you go beyond more than two levels. Okay. Now, if CPU addresses the cache and gets the data, then we said that CPU is supposed to have hit. Okay. In case it does not get the data, then we said it is just called a miss, that is it has missed the data, it is not available. So, obviously to see that the processor utilization is at its highest, the hit must be maximum. Okay, something like 90 plus percent, 98, 99% and so on. It means basically for every 100 times that the CPU accesses the cache, 98 or 99 times it is able to find the data that it wants. Okay. So, the higher this particular figure is, generally we talk about a hit ratio. Okay. The hit ratio obviously, as you can easily imagine, it is just the ratio of the number of successful hits, meaning the number of hits that meaning the CPU finds the data in to the number of total attempts by the CPU, that is what we said. Okay. 100 times the CPU tries to access, that is CPU is making about 100 attempts, and let us say if 98 times it is able to hit, then we talk about a hit ratio of 0.98. Otherwise, the same thing expressed is also 98%. Okay, fine. Now, the problem is what in case there is a miss. Okay. Now, in case there is a miss, then we know for certain that CPU cannot proceed because it does not find the data that it wants there in the cache. So, there is going to be some delay and this is going to cause problem. Fine. So, we say that associated with miss there is always a penalty that is associated, right. That is we talk about a miss penalty time, right. That is what exactly is the time taken, time taken to move in the new block of data that the CPU wants, fine. So, a block of data whatever that is passed on between two levels. So, the CPU does not find the required data in the cache, and so that particular block in which the CPU wants, that new block must be moved in, right. So, this miss penalty time is actually the time taken to, okay, why not write it, the time taken to replace. Why do we say replace? In fact, essentially what we mean is to move in. Okay, we may add that also. actually this is what we are interested, but then replacement automatically comes into the picture to move in the new block that the CPU wants, new block of data that the CPU wants, right. So that data which is available in this block can be accessed by the CPU. Okay. Now, in this process obviously it may be that the cache has to lose some contents, that is possibly the cache will have to lose a block of data and then that will be replaced by the new block of data. Okay. This situation may very well be there, because for instance you may say that CPU had accessed some data and possibly the data is no more needed by the CPU for subsequent processing, right, in which case it is meaningful to move out. So, normally what we say is we swap out, swap means exchange, okay, swap, but then we also say that the new data is swapped in, okay, you swap in the new data and you swap out the new data. So, we talk about swapping in and swapping out, though these are the terms that are used. Swap itself know that it means exchange, okay, you exchange two things, that is what swap is. So, we have to swap out the existing data and create place for the new data, new block of data to come in, which we say as swapping in the new data. Fine. Let us see how exactly this particular thing may be implemented, okay, from implementation point of view. Why? There are many issues related to this particular process of miss penalty, right. That is how exactly what exactly we want? We want to see that the miss penalty time is as low as possible, again from processor utilization, right. Earlier we said the hit ratio must be as high as possible, okay, that ensures the processor utilization. Similarly, in case there is a miss, this miss penalty time must be as low as possible, agreed, fine. So, what exactly must be the ratio? That is, suppose we have 1 k byte of cache, right, the DRAM may be let us say 4 k byte or 16 k byte and so on so forth, right. So, we will try to see what exactly is the way in which this can be implemented. Okay. We will take an example, we will arbitrarily assume, let us take a look at the chart. We will arbitrarily assume that the cache consists of course, there is only a simple example, let us say it consists of 10 locations, where the address cache address is let us say 0 through 9. Now, just shown as 10 locations, for instance you can even look at it as 100 locations or 1 k locations or 10 k locations or whatever it is, right. Assuming for this particular discussion the cache consists of 10 locations 0 through 9 and the main memory, that is the DRAM part, consists of 40 locations, that is numbered 0 through 39, there are 40 locations. Now, if the cache arrangement is such that as shown in the figure, at any time cache location 0, okay, will consist of data from main memory locations 0 or location 10 or location 20 or location 30, very simple arrangement, right. That is, into this particular location only the data coming from either this or this or not either, the data coming from this or this or this or this location alone can go in. For that is, there is it is not arbitrary, that is arbitrarily the contents of a memory location cannot go into anything else. So, similarly you just take cache location 2, into this the Main memory location contains the location being 2, 12, 22 or 32 alone can go, right. Now, this arrangement in fact is called a direct mapped cache. Direct mapped cache mainly because, as you can see, there is a specific relationship, okay, given a particular memory location address, then immediately we can say what is the cache location address. So, this arrangement is called a direct mapped cache, meaning a cache location can have only one of say n specific, okay, one of n specific location contents. Okay. Now, let us just look at the chart again. Suppose the CPU places the address 22. Now, why do we say address 22? Because as far as the CPU or the user is concerned, okay, the cache is something in between, in the sense the user knows that there are only 40 locations. He is not really bothered about the cache arrangement, it is coming in between. It has been arranged so that the CPU may interact with a fast memory which is a cache memory. Okay. Now, from user point of view, that is from programmer's point of view, he will imagine the system to be having 40 locations. He will not really bother about these 10 addresses, right. So, from programming point of view, the user is permitted to use any of these addresses, and they are also physically available, though in a slow memory. Okay. So, as part of the program which the CPU places instruction after instruction, the CPU will only have to deal with the main memory addresses, right. It is an internal arrangement that the main address memory will be mapped on to the cache as per some algorithm. Now, in this direct mapped cache arrangement or the algorithm associated with that, there is a specific way, and it is the easiest way. You can easily see, all you have to do is drop the most significant digit in it and you get the cache address straight away, but there is a way to work it out. We will look into it a little later. Now, suppose the CPU places the main memory address, let us say 23. So, from 23 the cache address, namely 3, must be derived, all right, it is not much of a problem. So, the CPU while executing the program, okay, will come across an address which in fact relates to the main memory address. Now, that is number 1, you must remember, but though the CPU may place the main memory address, the CPU will look for that information only in the corresponding cache location, because that is the fastest way to do it. Okay. In case it is there, fine, in case it is not there, then we talk about the miss penalty. Good. So, CPU places the main memory address, okay. CPU places main memory address, and from this particular address the cache address will have to be derived, cache location address or cache memory address, whatever it is. Okay. The cache location, the one will have to be derived. Now, that depends on the specific arrangement that you have. Now, let us see how it is. How will it derive? Okay, we have to have this algorithm. Generally, we can say this cache address, okay, cache address for the arrangement which shall we have that chart back again? Okay, we will take a look at the chart again. Take a look at it. The cache address will be derived like this. We can say this the algorithm, of course, it is easiest to derive in this particular case. Okay. Essentially, there is a way, you know why. I will give another example, then you will know why it is so. So, this particular one will be given as there is the arithmetic related to this will be, there is the algorithm related to this will be modulo, then the number of cache locations. Okay. Shortly explain what is all this, cache modulo that particular thing, and then you take the main address, that is the main memory address, that is what it is. Okay, you have to take modulo of this and then the main address. In other words, take a look at the chart, you will see that we have number of cache locations, how many? 10. Okay. So, in our case it is say mod 10 of the main address. See, the main address in case it is 23, from this 3 will have to be derived. As I said, in this arrangement it is easy, straightforward, but then we need to have an algorithm, and that is what we are working at, because we will see shortly what it is. What is this mod 1023? This actually means, okay, this is also called remainder arithmetic or residue arithmetic. This is nothing but saying take 23 divide by 10. Okay. Now, what is the remainder? Quotient of course is 2 and the remainder is 3, right. Quotient is 2 and the remainder is 3. So, mod 10 actually refers to that particular remainder, which is 3. This is how the cache address is derived. Just take a look, no problem. The chart you can see, of course, straightforward. 23, you know that if you drop these 2, then you get 3. Actually, the way you are getting it is by this particular one. Okay. The same way, suppose we have 26, then 26 divided by 10 will be 2 and the remainder will be 6, and that particular 6 will be the cache address. Agreed? So, that is what this particular thing is. So, as I said, this direct map cache, this is what you have. Now, let us take a look at another example. So, another chart we will have, the next chart, in which slightly I am varying, let us take a look at the chart. In this you can see it is not directly derivable, mainly because you have only 8 cache locations and then address, of course, for sake of simplicity I am giving the decimal address, right, and subsequent addresses will all be serially numbered, right. Now, you see up to 7 is all right, no problem. Now, you must have some method, it is not by dropping this most significant digit you can get the cache address. Now, what is it that has to be done here? The same formula you follow. Now, except that in this we said earlier cache address is modulo number of cache location. Now, in this the cache location is reduced to 8. So, it is mod 8 we have to take. So, let us take some example. What is the cache address for the main address, that is in this case mod 8, main address let us say is say 21, okay, main address is 21. So, as per the previous one we would get what, essentially 21 by 8 we will have 2 and the remainder is 5, right. Just take a look at the chart. For 21 you would get 5. So, that is what it means. Okay. So, this particular one is derived like this. So, this is the cache address, agreed. Okay. So, there is some mapping that will have to be done, okay. There is a mapping that will have to be done between the main memory address and the cache memory address, all right. And even this particular second example is also, okay, take a look at the chart, this also is a direct map cache. Why? Mainly because what it says is, if you take any specific location, that cache location can consist of data from these specific locations only, that is of the main memory, okay. Of the main memory location addresses 3 or 11 or 19 or 27, only these can go in there, that is why we say it is direct mapped, okay. Good. Instead of deriving like this, we can also have the same information in another form, maybe in a tabular form or whatever it is, okay. So, now when many memory locations can be mapped on to the same cache location, then that information must also be available, okay. So, one thing is to derive the address, another thing is, suppose, okay, you go the reverse way. Shall we take a look at the chart again? You go the reverse way. Suppose you see cache location 3. Now, location 3, cache address 3, what does it contain? Does it contain memory, the contents of memory address 3 or 11 or 19 or 27? How is it, how is that to be got? Where is? So, we have to store that information, because any time either the contents are either 3 or 11, I mean not either, contents of 3 or 11 or 19 or 27 will be there. Now, proceed the other way. What does cache address 3 contain? So, there must be extra information, otherwise we would not know, we will only know that one of these is mapped on to it, that is all, right. So, that information must be there. And then to start with, let us say right at the beginning, before anything else is started, the system is just switched on. What does the cache contain? We do not know. The cache may contain some trash information, that is some bits which may not be related to what we want, it may not be related to the data that we want, okay. Then we say that the cache to begin with contains invalid data, right. Only subsequently when from some blocks of information are moved from DRAM to cache, then we talk about valid data being there, okay. And in this example, take a look at the chart again. In this example, we know that contents of this or this or this or this can be in this, any one of these is valid, any one of these is valid. Now, which one of these we must see, okay. Now, to start with, that location 3 may not contain anything, it may not contain any of these, it may contain just like that, because power on, what can you say, it will be arbitrary, is it not. So, the cache contents, okay. So, actually we have to worry about what are the things that must go into the cache memory. In other words, what are the cache contents? One thing that we know is it will have the data, that is the data that is required, which comes from the DRAM, okay, that part is okay. The other thing is it must have some extra information which indicates which part, okay, this particular data is from which part of the DRAM, which part of the main memory. The earlier we saw it could be one of the 4 locations. So, which one, okay. So, that information is given by what is called a tag, okay. So, the cache must include the actual data, it must include the information about which part of memory it has, tag, and then another thing is there must be at least one bit of information which says that it is a valid data or that it is not a valid data. So, in other words, the format of the cache contents consists of 3 fields. What is this? The actual data, a tag information, and then the valid field. So, we talk about 3 fields: valid field, tag field, and data field. Valid bit is just only 0 or 1, just only 1 bit will do. The tag will depend on our mapping. Okay. For instance, shall we take a look at the chart again? For instance, so this location 3, so it has to say whether it is this or this or this or this. Okay. That is, in other words, whether the data from this row or this row or this row or this row is there. That is, basically we need to have say 1, 2, 3, 4 as 4 these things. So, 1 means this, 2 means this, 3 means this, 4 means this. So, this tag information, if it is there, then we know which one of the 4 is actually there, that is what we mean, and then the actual contents of that location. Okay. So, while trying to improve or increase the CPU utilization, see what all is happening. Number 1 is we talk about hierarchies of memory, and number 2 is once you say that cache will be of reduced size, but it will be very fast. When it is reduced size, then we have to say which part of the main memory is in the cache, okay, and so on. So, now you can see, though essentially CPU is going to deal only with the data, okay, but it must also have this information because of the internal arrangement. Now, the user is blissfully unaware of these things, this is important, the programmer need not really bother about this, okay, fine, this is all for the designer, so to say. So, this valid bit will be usually 0 to start with or initially, okay, and then later on whenever this particular block is used, block basically means just one unit of information, it can be any number of bytes, we will talk about it. So, for that particular block of data that is there, whenever the relevant data comes from DRAM, then the bit valid bit will be set to 1, okay, I am talking about the valid bit set to 1. So, we may say it will be 1 when in use, okay, when this thing is in use, then it will become, it will be set to 1. Now, why don't we take an example and then work out, right. Suppose in cache location, okay, let us say 2, am I right? Yeah, 2. In cache location 2, the data from main memory location 32 is already there, okay. Then we would say the valid bit is 1, and whatever be the data in memory location 32, okay. So, I just refer to as the contents of memory location 32, that will be the data, okay, that would be there in the cache 2, and what will be the tag 32 will always get mapped to 2. Why don't we take a look at the chart and then see. Memory location 32 will always be in location 2, and the tag that it will be referred to will be by some number. What is the tag? 3, okay, 3 we will identify, no. In other words, in this of course simple arrangement, the tag 3 and cache location 2 in fact gives also clue about the memory location being 32. So, a tag which will uniquely identify which of the 2, otherwise, so let us say for instance the tag were 1, then the data contents would have been from location 12, that is what it means. Good, fine. Suppose the Let us work out the relation between these. Okay. Suppose the CPU generates the sequence of addresses like this. That is, the CPU is generating the main memory addresses, okay, assuming it's first it generates 22. It's a little arbitrary, then it generates 23, then 17, then again it generates 22, okay, and then again 7, and then 17, and then 22, and so on. Okay. Now, what exactly is happening? CPU is generating these main memory addresses, and what will cache contain for each of those instances? Let us work it out. Okay. So, first we start with the sequence of memory addresses, that is the main memory, that is what we mean, okay, main memory addresses, and then that is the sequence we will write down, and then what is the corresponding cache address, okay, and then we will see whether this particular process had resulted in a hit or whether there was a miss, okay, and then also note down the corresponding valid bit, then tag bits, the field whatever it contains, and of course the data part we know roughly what it must be, fine. Now, actually these are the contents of the cache, right. This for us actually to follow the other things. Now, we will start. The first one is CPU generates the address. Let us say this is to begin with. To begin with, this is the very first address that the CPU generates, 22. Okay. Now, the cache address is 2 as per our arrangement, okay, and to start with, right, cache location 2, what will be the valid bit? The valid bit must be 0, because it is just to start with, the cache does not contain any valid data. So, initially it would have been 0, right, and by looking at it at the cache contents of 0, the system knows that the cache does not contain the required data, and so the contents from location 22 must be brought into this part of the cache, right. So, whatever may be the data, so we will just say okay, that we will just record, maybe 22 was containing some number, whatever, it does not matter. So, location of 22. Now, what about the tag? The tag is, remember the algorithm we were calculating, maybe we will take a look at the chart again, okay, and then see, that is we are talking about location 22 and it is in cache location 2. So, the tag must be 2 to indicate that it is from 22 memory location, we have it in cache location 2. So, the tag must be 2 in this case, right, good. So, that is the tag. Now, having got this, what about the valid bit? Now, the cache contains a valid data, right. So, this valid bit must be that 0 must be removed and the current content must be 1. Now, before going into it, the CPU really missed the data, is it not? So, this is a case of miss, and having missed it, it brings in the contents from location 22 and then brings a and then sets this valid bit as 1. Okay. Now, just for argument's sake, suppose the next CPU address is also 22, then fine. By looking at the valid bit and tag 2 in cache location 2, from tag 2 and cache location 2 will give the address as 22 and then valid bit is 1, and so which means already the data is available from location 22. All right. Now, let us get back to the problem. Now, after 22 the CPU generates the address 23, fine. Now, let us put down that is the next address 23. So, 23 will be in cache location 3, fine. Now, is 23 now recall the cache contains initially nothing. Right now all we know is that in location 2 it has a valid data, that is all. So, now for cache location 3 as before it is a case of miss, right, and the valid bit would have been 0 because nothing was brought in earlier, and now the tag will be 2 as before, and because there is a miss penalty cycle must be gone through and the data from location 23 must be brought in, fine. So, that is the next case. Now, after 23 17, well, now must be quite familiar. So, for memory address 17 we have to look into the cache location 7, and again it is a question of miss, we do not have this data from location 17, and so that is indicated by valid bit 0. Oh yeah, we forgot, after the previous one was brought this valid bit must have been set to 1, right, forgot to mention that, good. Now, so the data from location 17 is brought in, right. The tag for this in our previous case, I think in our simplest case first one it would have been 1, okay, that is the tag bit, and having brought this valid information this is set as 1, the valid bit is set as 1. Now, after 17 see here 22 the CPU generates the memory address 22 and the corresponding cache location will be 2, okay. Now, the corresponding cache location 2 we already have a valid information, right, and what is to be checked is the tag, because cache location 2 can contain memory location contains 2 or 12 or 22 or 32. So, it is the tag which is going to indicate that it is 22 and not the other things. Now, we find that there is a valid bit and the tag is 2, which means the data field contains location 22. Now, for the first time I think we are coming across that the required data, that is the data required by the CPU is available, and so it is a question of hit no change, it is already available, that is valid bit is 1 as before, tag is 2, and for the first time CPU fetches the data which is already available in the cache. And what is the data available in the cache? It is from memory location 22, all right. Next we just took it as 7, right, CPU generates the address 7. Now, CPU 7, and what do you have in 7? Cache 7 cache location 7 we have a valid bit, okay, but look at the tag bit, it says 1. What does it mean? For in cache location 7 if the tag bit is 1 it means actually it is the contents of location 17, but what is required is 7, is it not? A corresponding cache this thing is also 7, right. So, in location 7 we have the contents of 17, but what is required is from 7, right, and so this is also a question of miss, even though you find that the valid bit is 1, okay, mainly because the tag shows that it is not from location 7, but from location 17, okay, which is what we had worked out. Okay. So, this is also a question of miss. Now, into this cache location 7 the data from memory location 7 is brought, earlier it was containing data from memory location 17. Now, 7 is brought and the tag corresponding to this is 0, okay, and valid bit is 1. For a moment just take a look at this. Memory address 17, cache location 7, memory address 7, cache location 7. So, these two are distinguished only by the tag, right. The contents of 17 in this situation, that is indicated by tag 1, the contents of memory location 7 is indicated by tag 0, fine. So, this is a question of miss again, good. After 7 we have 17, good. What is that? Right, again the cache location is 7. Now, valid bit corresponding to 7 is 1, right, valid bit is 1, but what is the tag? The tag shows 0, which means from memory location 7 and not from 17 or 27 or 37 is available. And so, this is also a question of a case of miss, and from memory location 17 the data must be swapped in and the tag must be set to 1 to indicate that it is 17 and valid bit is set as 1. And in our example we have taken after 17 22 as the next address generated by the CPU. For 22 the cache address is 2 and see here 2, valid bit is 1 and the tag is also 2, which means currently the cache location 2 contains the contents of memory address 22, which is already there. So, this is a question of hit, okay, and there is no change. 22 the tag will be set as 2, the valid bit is set as 1. Now, like this when you proceed you will find that we are not done for all the cache locations, as it is we are seeing for 2, 7, 3, okay, these are the only 3 locations we are seeing, that is because of the example you have taken, right. So, for these 3 locations it is indicating the valid bit, tag bit and data bit, data bits actually, right, the 3 fields. Now, you can see after you proceed after some time the valid bits will all be 1, that means the respective cache location contains some valid data, precisely which location that is indicated by the tag, okay. That is the sequence in which this cache is participating in, okay. Now, so now one thing is the cache contains other than the data bits, it also contains the tag information and also the valid bit information, right. And as I said for location 2, cache location I mean 2, 7 and 3, right. These are the 3 cache locations and we are seeing that those cache locations will be containing this information appropriately, okay. These are the one, because the previous one would have been changed, right, that is what it is, good. Now, let us work out one more example. Suppose we have been given that we deal with 32-bit data, okay, 32-bit data, and the CPU generates also a 32-bit address, okay, we need that information also, 32-bit address. We will assume that the memory is still byte addressable, okay, byte addressable, and so the data if and whenever the CPU wants can also refer to any 8-bit of this data, okay, that is the idea. Now, the problem is we will assume the same direct mapped cache. So, the question is in a direct mapped cache, okay, in a direct mapped cache, that is the same arrangement, we are not changing that. In a direct mapped cache, if you have this information, then how many total bits are required in the cache, that is how many total bits. Why? Because the cache contains different fields. Specifically, we know it contains data field, tag field and valid field. As far as the data field is concerned, we know that it is 32 bit, but what about the tag? What about the valid? Valid also we more or less know it is going to be 1 bit, but what about the size of the tag field? That has got to be worked out. That you will see will be worked out from the 32 bit address. So, in this cache, how many total bits are required? Okay. We will assume one more thing, that is the cache size. Okay. For a cache of let us say 64 kilobytes of data alone. Okay. Data has been given, that is the data part. This part has been given as the size 64 kilobytes. Now, apart from this data field, we also have these fields. Essentially, we are going to work out the size, okay, 64 kilobytes. So, now we know this much, that we have to accommodate for the valid bit, okay. Then we have to accommodate for the tag bits and the data part. What I will do is, I will assume that the block of data is still 32 bit. Okay. No harm, we only said a block of data is the minimum unit which passes between two levels. That unit can be any size, right. So, I will assume 32 bit data is there in each cache location, which means as actually 4 bytes, right, that is what it means. So, the data field is 4 bytes and that accommodates for 32 bit. So, I will just say this, just call it as byte 1, this as byte 2, this as byte 3 and this as byte 4. So, I am assuming the block of data as 4 bytes. Now, since it is given that the cache is of 64 kilobytes and you have 4 bytes in each block, now I know how many blocks are there. That must be 64k by 4, which is there must be 64k KB, that is kilobytes, by 4 bytes each, and so we will be having how many? 16, right, 16 kilo blocks. So many blocks are there, 16k blocks are there. That is what we are talking about, is 16,000 blocks, right. Good. Now, let us take the address and work out the other things. The valid bit we do not have to discuss much, because if the data is valid, it is going to be 1, otherwise it is going to be 0. So, the valid bit, the valid field size is only 1 bit. Now, the tag is what we have to work out, which we will have to work out from the address generated by the 32 bit address size. Okay. So, let me say, suppose I have this 32 bit address, 32 bit address, okay, starting from bit 1 to bit 32. So, that is just the address size, starting from bit 1 to 32. Now, what did I assume? Each block has 4 bytes, is it not? And then I have to accommodate 16k blocks, right, instantly. What is 16k? How do you compute? 16k is actually 2 to the power 14, is it not? Just work out if you have any doubt. Okay, 16k will be 2 to the power 14. So, I need to have a 14 bit vector to indicate that there are 16K blocks, okay, fine. And then once I know which block, since I said it is a byte addressable, I should also know which of the byte if necessary. If it is only 32-bit data, no problem, okay. It is enough if I identify the block number. But if I also want to know which of the byte, I need to have at least 2 bits to identify this one of these 4. So, in the address I have to allow for 2 bits. Let me say I allow these 2 bits, okay. This particular 2 bits is for indicating which of the byte. So, this 2 bits are called byte offset, that is what are the combinations possible, 0 0, 0 1, 1 0 or 1 1. So, one of these 4 will identify whether it is this byte or this byte or this byte or this byte, right, fine. Now, once I have identified which byte, then next thing is I have to identify which block, for which I need 14 bits, right. So, the tag part of it, the block offset part of it, that is the next one, 14 bytes, that is 14 bits, that is starting from 3 to it will be 16, right, 3 to 16, so many bits. So, these 14 bits will identify 14 bits, okay. These 14 bits will identify which of the 2 to the power 14 blocks, that is one of 2 to the power 14 blocks, right, good. Now, that this one 14 bit thing is called a block offset. So, we had allowed 2 bits for byte offset and 14 bits for block offset. Now, what is remaining? The remaining you have 2 gone here, 14 gone here of 32, the remaining is 16, right. So, this is what is used for tag field, okay. So, the tag size will be 16 bits. So, 1 bit for valid, 16 bits for tag field, and for data we already assumed, right, how much, 4 bytes, so 32. So, 32 plus 16 plus 1, that is essentially you have got 49 bits, right, just add this 49 bits. So, this in fact is the size of the cache, meaning 49 bits by 16K, okay. So, because there are 16K blocks each of 49 bit. Now, one important thing you have to notice is essentially 49 bits includes 32 bit data. So, we need this extra thing basically to keep track of which part of memory address is in any cache location. This of course specifically for the direct mapped cache organization, right. For different organization you will have different way of working out.